Hello everyone, how are you? So in the last lecture we finished the chapter number 5 on MOSFETs. In that chapter we mainly talked about the structure of the MOSFET, the physical operation of the MOSFET, how to induce a channel, how to flow the current, its different modes of operation, cutoff, saturation, triode regions. We also talked about the enhancement mode and the depletion mode. We talked about how we can use the MOS transistors in the DC circuits. We okay, so now we are kind of jumping to chapter number 7, which is on transistor amplifiers, and we will only cover the contents of this chapter that are related to the MOS and MOSFETs. Then we will go back and discuss the BJTs, chapter number 6, and come back again to chapter number 7 for the BJT amplifiers. Okay, so with that, let's start with chapter number 7, transistor amplifiers. I am going to give you a very brief summary of the important concepts of chapter 5 of MOSFETs that will be used or will provide the basis of this transistor amplifiers topics of chapter 7. Right, so here is a summary for the NMOS transistor, enhancement mode transistor, in which we have to create a channel or induce a channel at the start. Here is the symbol, source, drain, gate, right? So we initially apply a gate to source voltage that should be greater than the threshold voltage to induce a channel first. Less than the threshold voltage, right? When it is less than the threshold voltage, no induction of a channel, no creation of a channel, no flow of current. Now, once the channel is induced and we apply a VDS, a drain to source voltage, for us very small values of drain to source voltage, channel behaves as a linear resistance, whose value is given over here. Kn inverse of the conductance, Kn dash W over L VOE. And we saw that as we increase the drain to source voltage, the channel will no longer remain as a linear resistance, but its resistance will increase. Why? Because our channel will start to become tapered rather than a uniform rectangular channel. Our channel started to become tapered and then continue to become tapered. At this point, it will be pinched off, and this point is when drain to source voltage will become equal to the overdrive voltage, right? So this is the point. So at this point, the channels enter into the saturation region. So condition for the saturation region is over here. Condition for the triode region is over here. This can also be alternatively represented by the gate to drain voltage. For a triode region, the gate to drain voltage should be greater than the threshold voltage, and for the saturation, it should be less than the threshold voltage. Or you can represent that in the terms of a drain to source voltage. For saturation, it needs to be greater than the overdrive voltage, and or equal. Equal point being is the start of the saturation region. And here are the values of the drain currents for both the saturation and the triode regions. We also saw this VI characteristics for the NMOS transistors. Here is VDS, here is drain current. And as you are increasing this overdrive voltage, you saw that we get this curve, right? And the value of this drain current depends on the overdrive voltage, right? So this is the same curve as seen over here. Now, as you are increasing the overdrive voltage, the drain current will increase, and that is why you get the higher values of these plots. Okay. Now, interestingly, you will also see over here that this also shows a IV characteristics with respect to the overdrive voltage or gate to source voltage. So then we saw characteristics for the drain current to gate to source voltage. Now, as the gate to source voltage increases beyond threshold voltage, less than that, no induction of the channel, so current is 0. As soon as it is greater than the threshold voltage, we saw this a square law relationship in between the drain current and gate to source voltage, which can be shown by this equation. this equation or this equation, right? So here's an output drain current. Here is your input gate to source voltage, and we see that the drain current increases by the square of the input gate to source voltage. We also saw or discussed that in order to operate transistor as an amplifier, we have to operate that in the saturation region, and this will form the basis of this entire chapter number 7 MOS amplifiers topic. We also discussed that this is in the saturation region, MOSFET operates as a constant current source which is controlled by the voltage. Over here, this is our voltage. It's a voltage controlled current source, ID. We also made a equivalent circuit of the model in which this is our input voltage. Here is a constant current voltage controlled. Voltage is VDS. And we saw that our output resistance was infinite, right? So this was neglecting the channel length modulation effect, in which we are saying that at pinch off, our drain current becomes saturated and becomes constant, right? For all of these values. We saw that in saturation, the current becomes constant, right? So our slope is 0 and our resistance is infinite. However, then we saw that this is not entirely true, and beyond pinch off, our length of the channel beyond pinch off, as our VDS increases greater than the overdrive voltage over here. Now at this pinch off occurs, beyond this point, when VDS starts to become greater than the overdrive voltage, the pinch off point will start to move from here, move towards the source region, and our length of the channel will reduce. As our length of the channel will reduce, our current will increase, and going back over here, we saw that our characteristics will be slightly increasing rather than a constant, and now this indicates a positive slope. So we are going to have a finite resistance. So we ended up making this model in which we have a finite resistance. And this effect is known as a channel length modulation effect. Channel length modulation effect. Okay, so this is the overall summary of all the previous concepts from chapter number 5 that will form the basis for chapter number 7. Now we are gonna jump to chapter number 7, transistor amplifiers, and we're gonna start with how we can use NMOS transistors to make a voltage amplifier, and we will also talk about different configurations we can make out of that voltage amplifiers, out of those NMOS. These will be we will also talk about the small signal models of the voltage amplifiers too. Okay, so let's start with the kind of a basic principle. We just discussed this basic principle that when a MOSFET is operated in the saturation region, our gate to source voltage can be rewritten as can control the drain current, which is provided by this equation. Here's output drain current, here's input gate to source voltage, and this is a square relationship. One more important distinction over here is that in this chapter, we are introducing another term, which is an alternative term for the saturation region. It will be known as an active region. We are going to use this interchangeably. That saturation region for the MOS transistor is also known as an active region. And this will become more clear in the next lectures. Okay. So we have a square relationship for the VI characteristics for this amplification. When we operate that MOS transistor as an amplifier, our drain current has a square relationship with the gate to source voltage, which can serve as an input voltage applied at the gate terminal. So our transistor can behave as a transconductance amplifier. Transconductance amplifier means that our input is a voltage, right, and our output is a current, so it can behave as a transconductance amplifier. So we are going to talk about how we can build a voltage amplifier out of this. So here's a circuit, here's a kind of a representation of an NMOS when it is operated in the saturation region, right? So this is a gate to source voltage, and we know that our gate to source voltage needs to be greater than the threshold voltage for the transistor to operate, otherwise it is in the cutoff mode. The other important thing over here is here's the equation. So when you will vary the gate to source voltage, this will vary the drain current, and this drain current will be varied. That is going to flow from drain to the source. In order to operate the transistor in the saturation region, we have two conditions. One of the condition is either this is essentially one the same, representing two different ways. Our drain to source voltage needs to be greater than the overdrive voltage, right? So either this condition needs to be true or this condition needs to be true. You can look at that two different ways. Our gate to drain voltage should be less than the threshold voltage. This means that the channel will be pinched off. Okay, so when the gate to drain voltage is exactly equal to the threshold voltage, it's pinched off. Or when the drain to source voltage is exactly equal to the overdrive voltage, it is pinched off, or at the edge of the saturation. Okay, so this is the overall potentials across the NMOS transistors to operate that in the saturation region, and we're going to see that this is how we operate that in the when we will operate the transistor in the amplification circuit too. Okay, so this figure is for the active region and or the saturation region. Again, we are going to use these words interchangeably. Our VDS voltage is greater than the overdrive voltage for it to be valid for the saturation region, or gate to drain voltage is less than the threshold voltage, right? So this one condition and the second condition we just talked about. An important thing again is that this is a non-linear relationship, right? So going back to this is a non-linear relationship. However, if you will remember some of the discussions from chapter number 1, that we are interested in making linear amplifiers to make sure that we have a linear amplification for the entire signal, right? So however, this is a non-linear amplifier, so we will discuss in much detail in the subsequent lectures that how we are going to build a linear amplifier out of this non-linear relationship. Okay, so let's start from how we can build a voltage amplifier. So we just said that it's a transconductance amplifier in which our output is a drain current. So how we can build a voltage amplifier out of this relationship, right? So here this is what is happening. If you look at this equation, the drain current equation, we are changing the gate to source voltage. You can consider that as an input voltage to an amplifier, right? So we are changing the input voltage to an amplifier, and our drain current is changing. So how we can obtain an output voltage, right? So very simple. You can just pass that current through the resistor and take a voltage across it, right? So the potential drop across that resistor will be proportional to the changes in the drain current, because our resistance is going to be the same, right? So this is how we can build a voltage amplifier. Okay, so transistor is a transconductance amplifier. So how to make a voltage amplifier? Just pass this output current, which is a drain current, through a resistor, and the potential drop across the resistor will be proportional to the changes in the drain current. So that will be the output. So let's look at this circuit now. In this circuit, we are doing exactly the same thing. This is our drain current. So we are flowing the drain current through this constant value of the resistor. We are going to call this resistor as a load resistor or a load resistance. Okay, so we are flowing this current through a resistor, and whenever we will make any changes, any variability in the gate to source voltage will translate into the changes in the gate to source voltage will be translated into the changes in the drain current, right? And that will end up being changing the value of this product, IDRD, right? So the potential drop across IDRD will change. Now we could have so another important distinction that you can see over here, rather than taking an output across V0 over here, we are taking this V0. Our V0 is equal to VDS. We are taking an output across the drain to source terminal, rather than taking an output directly across the resistor. So why we could have done it the other way as well. The most important thing over here, or the advantage of taking the output as equal to the VDS, is if you look closely over here, we have a common ground. right? In between the source, in between the input and the output of the amplifier circuit, we have a common ground, right? And making a common ground in the circuit simplifies the circuit a lot. And we will see that when we this configuration will allow us to use transistors and in cascaded configuration, many other configurations. So having a common ground in between input and the output really helps a lot in circuit simplification, circuit building. So that is why we ended up taking an output rather than across a resistor, across the drain to source terminals as a VDS. Now we will see that our basic concept will remain the same. What is happening now is still our changes in the VGS. Our changes in the VGS is translating to the changes in the current. That is changing the drop across the resistor IDRD. So our output will change accordingly, and we're gonna drive an equation for that. Okay. So you can NMOS, a simple NMOS amplifier is shown in this circuit where VGS is the input voltage, right? So you can consider this VGS as the input voltage. This RD is known as a load resistance, right? So the changes in the drain current ID will eventually producing a change in the potential drop across this resistance, which is IDRD. And we will see that, and this is the supply voltage. VDD is the supply voltage that is going to power up the amplifier, and this voltage and the value of this resistance is going to establish whether this transistor, in which region the transistor is operating, and how we can make sure that it is operating in the saturation region for the amplification process. This will become more clear in the next few slides. Okay, and this is what we just talked about. Rather than taking the output across a load resistance, we are taking it as VDS to provide a common ground for the input and the output. Okay. Now, so let's write down this equation for the output voltage, right? So we know that if my equation for the ID will be equals to VDD minus VDS over RD, which is equals to IDRD equals to VDD minus VDS. So if I have to take the VDS out, VDS equals VDD minus IDRD, right? And this VDS is also equal to V0, right? So this is the relationship of the input-output relationship of the amplifier. Now you can see that this, and of course this depends on the gate to source voltage. So as you are changing the gate to source voltage, your drain current will change. This drain current ID will change, so the potential drop across IDRD will change, and that will change the output voltage. So this is how we obtain a voltage amplifier, even when we are taking an output voltage as the drain to source voltage. Okay. So this is the equation that we just derived by solving a simple circuit. Okay, so note down this inverted relationship, right? And this is what we just talked about. So what is happening is, as our gate to source voltage is changing, this is changing the drain current. However, when the drain current is, for example, increasing, when our drain current, for example, increase, this IDRD product will go down, right? So when ID will go up, the product IDRD minus of IDRD will go down. So this means that, this means that VDS will go down. So that is why it has an inverse relationship with ID, right? So it's gonna put the VDS as an output voltage, and ID, which is controlled by VGS, input voltage, is going to follow an inverse relationship. And this is what we can see over here from the voltage transfer characteristics as well. Okay, so in terms of our voltage transfer characteristics, again, our input is a gate to source voltage. Our output is a drain to source voltage, right? So this is V0. And so this is something looks like this. Now let's delve deeper into this plot. We are going to discuss how we can build this thing, okay? Again, so on the x-axis you have your input voltage, gate to source voltage. On the y-axis you have your output voltage, drain to source voltage. And now let's see. Okay, let me kind of start over here, and then I can rub this out. So this is the input voltage, gate to source voltage. So let's make our own voltage transfer characteristics. So on the y-axis we have an output voltage, and on the x-axis we have an input voltage. Okay, so what will happen when our gate to source voltage is 0? So we know that when gate to source voltage is 0, this means that no channel will be induced and the drain current will be equal to 0. So when the drain current in this equation will be equal to 0, right? So this is our, let's call as equation A. If you, okay. So when the drain current in this equation will be equal to 0, this means that the voltage VDS will be equals to VDD. Okay, right? So this voltage is equal to VDD at 0 VDS. Now this will remain true, that our drain current will remain 0 till a point when VGS will become equal to threshold voltage. At threshold voltage, the channel will be induced and a drain to source voltage, and whatever the drain to source voltage that will be appearing is going to determine whether it is operating in the saturation and or the triode region. All right, but at the gate to source voltage, the threshold voltage, when the gate to source voltage will become equal to the threshold voltage, a drain current will start to flow. Now, so we can see that the VDS will remain equals to, so this VDS equals to VDD minus IDRD, right? So this VDS will remain equal to VDD till VGS in this region, till VGS remains less than the threshold voltage. So we get this region, right? Okay, so this region is called as a cutoff region when our drain current is 0, right? So this is a cutoff region. Okay, so what will happen at this point? So once this point will reached, once VGS will become greater than the threshold voltage, we know that when the VGS will become greater than the threshold voltage, so channel will be induced and the current is going to start to flow. As soon as that current will, as soon as the current will start to flow, as soon as this current will increase, the VDS will start to decrease, right? So now what is happening is the current is increasing and the VDS is decreasing till a point it will go down 0. Okay. Now we know that once the gate to source voltage can become greater than the threshold voltage, it can be operated into two different regions. One is the active region and or the saturation region. The second one is called as a triode region. So in this going down curve from VDD to 0, which one is the saturation? How to identify a saturation region and the triode region? One more condition that we know is that when our drain to source voltage will become equal to the overdrive voltage, it will enter into the saturation region, or this is kind of an intersection point in between the triode and the saturation region. So we can define that overdrive voltage over here. Let's assume that this point is equals to the overdrive voltage. Okay, so this means that at this point this will be our point of separation of the two regions. This is our triode region now, right? Because now VDS over here is greater than the overdrive voltage and over here it is less than the overdrive voltage, right? So this is a triode region and this is a saturation region or active region. And so let's call this point as a point A, this point as a point B, and this point as a point C. This point C is when our VGS will become equal to VDD and our VDS will again become equals to 0. Okay. So the important thing is, so this point, the voltages at this point will be VGS at point B, VDS at point B. Shortly, we are going to determine the values of this VDS at point B and VDS at point B, right? Okay. Now this is exactly the same curve that you can see over here. So I hope that this kind of doing it from the scratch is helpful for you to understand how these voltage transfer characteristics are drawn. Okay. So in summary, if you look closely over here, we still have 3 regions of operation. One region of the operation is the cutoff region. in which our VGS is less than the threshold voltage. As soon as it will become more, we saw that our current will increase and our drain to source voltage, output voltage, will decrease because of this drop. And it will continue to decrease till it will become equal to 0 at point C. However, to separate the saturation and or the triode region, we define this voltage, that this voltage is equal to the overdrive voltage. At this voltage level, we say that, okay, this is the separation point of the saturation in the triode region, and less than the overdrive voltage will be, when the VDS is less than this overdrive voltage, it will be the triode region, right? So this was a triode and this was a saturation. Okay. All right, so with this is all the points that I just talked about. So you will also get the slides. So don't worry about the text here. Okay. So another thing, important concept over here, just by looking at this plot, right, we can see that this is the region of operation in between points A and B where we can achieve high amplification, right? Over here the slope is smaller, and since we want a constant current, neglecting the channel and modulation effect again, we want to operate the transistor in the saturation region, right? And the saturation region has a higher slope, and the highest slope over here, what is the slope thing over here, right? It is the output over input. So our slope of this line, of this transfer characteristics line, is going to determine the amplification gain. So we want the highest slope. Now, if I will look even more closer in the saturation region line, I can see that even the slope is higher over here as compared to over here. Sorry, okay. The slope is higher, slope is smaller over here and higher over here, right? So this is the zero slope and this is the infinite slope, right? So our slope over here is higher and the slope over here is lower. So that is why if I will operate the transistor even more around somewhere over here, I can even achieve higher amplification, even in the saturation region. And we are going to discuss this point in detail in the subsequent lecture, and this is very important point. We're going to come back to this point multiple times. Okay. Right, so we want the largest amplification gain, so that is why we operate that in the region A to B. AB points, which is a saturation region or the active region. Okay, so another important concept is that during this amplification process, we want to make sure that our transistor will remain in the saturation region, will still remain in the section A and B, right? Its operating point will be confined to the segment A and B. We want to make sure that our transistor will operate in between points A and B, and it will not go beyond it, because if it will go over here, it is going to be in the cutoff region, or outside B, it is going to be in the triode region where slope is much different, and we're going to get a very nonlinear amplification values. So we want to make sure that our transistor remains in the section A and B, and even more closely over here. We're gonna discuss that in more detail. But here is an important thing. What we want to do here is we want to decide at which point are we going to operate the transistor even in the saturation region, such that when our input voltage vary, since we are going to have a time varying input signal for the amplifier, when our input signal will vary, our output signal should not go to the cutoff region and or the triode region. And this is what is known as selecting a bias point or operating point or quiescent point. And we are going to discuss that in sufficient detail in the subsequent lecture. And this, my earlier sentence will become more clear. How do we select a bias point or operating point of a transistor on this saturation region or voltage transfer characteristics? Okay. Right, okay, so its operating point should be remains in the segment A and B. Just we want to make sure that it will not go, our output will not go into the saturation, into the cutoff or the triode region. Now let's find out the expression of the segment A and B. The segment A and B is again the saturation region. So this was the initial equation. VDS is equal to VDD minus IDRD. This is the equation that is coming from here, right? And this is a drain current equation that we know that for the saturation region, ID is equal to half Kn VDS minus VT square. You can see that equation over here, or you can also see that in the summary slides, right? So this is a saturation current equation, or this one, replacing this value there. Okay, so, and all you need to do is to replace this ID value over here, and you will get this equation. Now this is the amplification, kind of an amplifier equation over here, which shows a relationship or inverse square relationship of the input and the output voltages, output voltage being VDS and input voltage being VGS. And this is a square relationship, and this is an inverse relationship. So inverse square relationship of input and output. Okay, so this is a nonlinear relationship because of the square thing, right? And our objective is to obtain a linear amplification. So we will discuss that shortly, how we can do it. So important thing is determining this coordinates of the point B, right? Which is a boundary between the saturation and the triode regions of operation, right? So important thing is, if we will find out these points, these are the points, so we can make sure that our transistor during the operation will not enter into the triode region, right? So these points are helpful in obtaining the linear amplification, not only just the linear amplification, but also making sure that our, during the operation of the transistor, when our input voltage is varying, our transistor will not enter into the triode region or away from the saturation region. So let's determine this point, the drain to source voltage at point B and the gate to source voltage at point B. Okay, so this is the equation that we just derived, this one, equation A. Okay, so let's find the drain to source voltage and the gate to source voltage. Okay, so in this equation, so what we are doing is we are, so our gate to source voltage is equal to the gate to source voltage at point B, right? And our drain to source voltage is the drain to source voltage at point B, and we know that drain to source voltage is equal to the overdrive voltage at that point, right? So this was a point of entry of the saturation or the intersection boundary point in between the saturation and the triode region, and we know that this will happen when our VDS is equal to overdrive voltage, right? So VDS at point B is equal to the overdrive voltage at point B. What is the overdrive voltage at point B? And we know that what is the overdrive voltage? It is VDS minus VT. So it is the gate to source voltage at point B minus threshold voltage. So what we are doing over here is that we are replacing this VGS by this value in this equation, and we are replacing this VDS by this value, VDS minus VT, that we just derived, right? So replace this value over here, and you ended up getting this equation. Essentially, if you're going to replace this out, you will realize that it will become a quadratic equation, and you can just solve it for the roots, and you can find out this equation easily. So this is the value of the gate to source voltage at point B. So we ended up finding out this value. Now let's find the value at VDSB. We just saw that VDSB is equal to VGSB minus VT. So if you do one more minus of VT, which will subtract these two terms, this will become your overdrive voltage. VDSB at the start of the active region, right? So this is your overdrive voltage, which is equals to, again, VDS minus VT. This was your original VDS. And if you subtract a VT from there, you can find an overdrive voltage. Okay, so this is the end of the small lecture today. And what we talked about, the main points of this lecture was, we ended up seeing that our transistor, which was a NMOS, which was a transconductance amplifier, how we can convert that into a voltage amplifier by passing that current through a load resistor. And now we are still taking an output, not across the load resistor, but across the drain to source, right? And this is just to make sure that we have a common ground in between the input and the output. Now our changes in the input voltage will be reflected in the changes in the drain current, which will change the potential drop across the load resistance, which will be reflected in this equation, right? So we ended up driving this equation, We also saw in detail how we can find out this voltage transfer characteristics. When the VGS, gate to source voltage, is less than the threshold voltage, we have this cutoff region. When our gate to source voltage increases from the threshold voltage, but will reaches to this point B, which is equal to the overdrive voltage here, it will remain in the saturation region, and beyond this point it will go into the triode region till point C. We also see that in order to operate the transistor as an amplifier, we need to operate that in the saturation region. So we need to select these boundary points of B such that our transistor will not go into the triode region, and we are going to explain in much more detail in the subsequent lectures. We ended up finding out this relationship by just putting the drain current equation from here to here, and then we derived the boundary points of the B. Okay, with that we are going to end the lecture here, and we're going to talk more about how we can select that bias point, operating point of our transistor and the voltage transfer characteristics to operate that as a linear amplifier in the next lecture. With that, thank you so much. Have a good day. Bye-bye.